আলাইকুম। ডিয়ার স্টুডেন্টস, আজকে আমরা ক্লাসিক্যাল মেকানিক্স নিয়ে আলোচনা করব এবং আমরা নিউটনস ল নিয়ে আলোচনা করব ইনশাআল্লাহ। আমরা ফিজিক্স ভলিউম 1 5th এডিশন রেজনিক হ্যালিডে এবং ক্রেনের বই থেকে এই আলোচনাটা করব। আজকের আলোচনাটা একটু অ্যাটিপিক্যাল হবে। তার মানে টিপিক্যাল যে ক্লাসগুলো হয় সেগুলোর মতো করে আমরা নিব না ইনশাআল্লাহ। আমরা ইন গ্রেট ডিটেইলস ক্লাসিক্যাল মেকানিক্স নিয়ে আলোচনা করব। হোপফুলি সেটা তোমাদের কাজে লাগবে। তোমাদের আন্ডারস্ট্যান্ডিং এর জন্য সেটা হোপফুলি ফলপ্রসূ হবে ইনশাআল্লাহ। সো আশা করি তুমি আমার সাথে লাইভে থাকবে এবং পরবর্তীতে রেকর্ডেড ক্লাস দেখবে এবং এখান থেকে উপকৃত হবে। আমরা গ্রেট ডিটেইলসে আলোচনা করব। তার মানে ক্লাসটা ধৈর্য সহকারে তোমাকে দেখতে হবে যদি তুমি ক্লাসিক্যাল মেকানিক্সের কনসেপ্ট এবং নিউটনস ল বুঝতে চাও। Ancient philosophers were perplexed by the motion of objects. They wrestled with questions such as, do all motions require a cause? If so, what is the nature of this cause? Confusion about these issues persisted until the 17th century when Galileo and Isaac Newton developed the approach to understanding these motions that we call classical mechanics. Newton presented his three laws of motions in 1687 in his Philosophia Naturalis Principia Mathematica, usually called the Principia. In classical mechanics, we focus our attention on the motion of a particular object which interacts with the surrounding objects, which we call environment, so that its velocity changes and acceleration is produced. Table 3.1, here in the book you have a table. So for this analysis, we will begin by treating physical objects as particles. So in physics, when we deal with these problems, we talk about particle a lot. What does particle really mean? Particle is the simplest object that you can think of. It's the simplest object which has motion restriction, which has different restrictions on it. So I will talk about that in a bit. By which we mean bodies whose internal structure or motions can be ignored and whose parts all move in exactly the same way. See, the particle in physics means this body whose internal structure or motions can be ignored. তার মানে এই বডিটার পার্টিকেলের হচ্ছে ভিতরের ইন্টারনাল যে স্ট্রাকচার এবং তার যে মোশন এটাকে আমরা হচ্ছে ইগনোর করে ফেলি। whose parts all move in exactly the same way. তার মানে এই বডিটার প্রত্যেকটা পার্ট হচ্ছে একদম সিমিলার ভাবে মোশনকে রেপ্লিকেট করে বা মোশন ঘটে। Often we must analyze motion of extended objects whose different parts may have different interactions with the environment. For example, a worker might be pushing on one side of a heavy crate while the bottom experiences friction as it slides along the floor. If all the parts of the crate move in the same way, we can treat the crate as a particle. চিন্তা করতে পারো পুরো একটা ক্রেটকে আমরা পার্টিকেল চিন্তা করতে পারি যদি ক্রেটের প্রত্যেকটা পার্ট সেম ওয়েতে মুভ করে, রাইট? সো এখন আমরা as a result, it doesn't matter where the environment acts on the object. Our main concern is with the net effect of all the interactions with the environment. Later in the text, we will encounter situations in which it does matter where we apply the forces to an extended object, but for now we will treat all the object as particle. So see, ক্লাসিক্যাল মেকানিক্সের একটা খুবই ইম্পর্টেন্ট কনসেপ্ট হচ্ছে পার্টিকেলের কনসেপ্টটা। যখনই তুমি ক্লাসিক্যাল মেকানিক্স নিয়ে আলোচনা করতে যাবা তুমি দেখবা সেখানে আমরা পার্টিকেলের কনসেপ্ট নিয়ে আলোচনা করতেছি সবার আগে। সো এতক্ষণ আমি পার্টিকেল নিয়ে আলোচনা করলাম, আশা করি সেটা তোমার উপকারে আসবে পার্টিকেলের কনসেপ্টটা। তুমি যদি এটার রেফারেন্স জানতে চাও, রেফারেন্স হচ্ছে রেজনিক হ্যালিডে এবং ক্রেনের ফিজিক্স ভলিউম 1 সেই বইয়ের চ্যাপ্টার নাম্বার 3। তুমি সেই চ্যাপ্টার নাম্বার 3 থেকে পার্টিকেলের যে ডেফিনিশন, যে রেফারেন্স দরকার সেটা তুমি পেয়ে যাবে। ওয়েল, we describe the interaction of a body with its environment. It means it in terms of a force. A force is a push or a pull in a particular direction. See, another important concept in classical physics is what we call force. Force কে আমরা কিভাবে ডিফাইন করি? It's a push or it's a pull. Force is either a push or a pull in a certain direction. Forces are described using vectors. For every force, we must specify the direction in which it acts, and forces must be combined using the rules for vector addition. I have talked about vector addition in great details in my other videos. You can watch those videos in order to learn vectors and the rules of vectors. The rules of vectors is very essential. It's at the core of the heart of classical mechanics. Well, in this chapter, we will consider mostly situations involving one-dimensional motion, in which case we must specify the force component, positive or negative, relative to that one direction. So each force that is exerted on an object is caused by a particular body in its environment. As you begin your study of classical mechanics, you may find it useful whenever you are analyzing the forces in a problem to describe each force by the body on which it acts and the body in the environment that is responsible for the force. For example, pushing force on crate by worker, or frictional force on crate by floor, or gravitational force on crate by earth. You will find this technique especially helpful when we discuss Newton's third law later in this chapter. To carry out our scheme for classical mechanics, we begin by defining the magnitude of a force in terms of the acceleration of a particular standard body upon which that force acts. We then assign a mass m to the body by comparing the acceleration of that body with the acceleration of the standard body when the same force is applied to both. Here, the text is talking about F equal to ma, that we define force with acceleration and then the mass term. We already know that, right? Okay, so force thus appears in both the laws of motion and in the force laws. The laws of motion and the force laws together make up the laws of classical mechanics. We all know that the Newton's laws are at the heart of classical mechanics. You must know Newton's laws in order to understand the mechanics of physics, classical mechanics of physics. This program of mechanics cannot be tested piecemeal. We must view it as a whole and judge its success based on the answer of two questions. Number one, does the program yield results that agree with experiment? Number two, are the force laws simple and reasonable in form? It is the crowning glory of classical mechanics that we can answer an enthusiastic yes to both of these questions. You see, what this book wants to say is that we can't really test out these laws, especially Newton's laws. So how do we know that these are correct laws? We ask ourselves two questions. Does the program yield results that agree with experiment? First things first. Second thing is that, are the force laws simple and reasonable in form? The answer is yes. For both of the questions, the answer is yes, and hence we can say classical mechanics is beautiful in its own way, and it's also true in terms of describing the motion of objects. So now we will talk about Newton's first law. Let me erase the board first. So now we will talk about Newton's first law. Newton's first law is pretty simple, but it's pretty tricky. It's very tricky, Newton's first law. Because in the Newton's first law, Newton himself actually defined inertial reference frame. In Newton's first law, he defined inertial reference frame. And you have to really understand that. You have to be really cautious about that. What does that really mean? Before Galileo's time, most philosophers thought that some influence or force was needed to keep a body moving. They thought that a body was they thought that a body was in its natural state when it was at rest. For a body to move in a straight line at constant speed, for example, they believed that some external agent had to continually propel it, otherwise it would naturally stop moving. So that was the time of Galileo. If we wanted to test these ideas experimentally, we would first have to find a way to body, free a body, okay, from all influences of its environment or from all forces. This is hard to do, but in certain cases we can make the forces very small. If we study the motion, as we make the forces smaller and smaller, we can gain an idea of what the motion would be like if the external forces were truly zero. Let us place our test body, say a block, on a rigid horizontal plane. If we let the block slide along this plane, we note that it gradually slows down and stops. This observation was used, in fact, to support the idea that motion stopped when the external force, in the case, the hand initially pushing the block, was removed. We can argue against this idea, however, by reasoning as follows. Let us repeat our experiment now using a smoother block and a smoother plane and providing a lubricant. We know that the velocity decreases more slowly than before. Let us use steel, smoother blocks and surfaces and better lubricants. We find that the block decreases in velocity at a slower and slower rate and travels farther each time before coming to rest. You may have experimented with an air track on which objects can made to float on a film of air. Such a device comes close to the limit of no friction, as even a slight tap on one of the gliders can send it moving along the track at a slow and almost constant speed. We can now extrapolate and say that if all friction could be eliminated, the body would continue indefinitely in a straight line with a constant speed. So here the book actually refers to, and it points to an example about how force is related to motion, right? So as an external force is needed to set the body in motion, but no external force is needed to keep a body moving with constant velocity. From the from the example that we discussed now, it is clear that a force is needed to set the body in motion, but there is no external force that is needed to keep the body in motion with constant velocity. It is difficult to find a situation in which no external force acts on a body, right? The force of gravity acts on a body on or near the earth, and resistive forces such as friction or air resistance oppose motion on the ground or in the air. Fortunately, we need not go to vacuum of distant space to study motion free of external force, because as far as the overall translational motion of a body is constant, there is no distinction between a body on which no external force acts and a body on which the sum and result or the resultant of all the external forces is zero. We usually refer to resultant of all the forces acting on the body as the net force. So the principle was adopted by Newton as the first law of his three laws of motion. Consider a body on which no net force acts. I repeat, consider a body on which no net force acts. If the body is at rest, it will remain at rest. If the body is moving with constant velocity, it will continue to do so. That is Newton's first law for you. That is Newton's first law. That is the statement of Newton's first law. I will talk about Newton's first law in great details in a minute. I will take a 2 minutes break and I will come back. So I'm back. Let's talk more on the first law of motion and reference frames. As I said earlier, that Newton's first law actually describes what a reference frame, what an inertial reference frame is, and it also actually gives you the very definition of inertial reference frame.